long, diameter, and 0.91 m, 36 in, wide. Flight Systems, Edit. The orbiter was equipped with an avionics system to provide information and control during atmospheric flight. Its avionics suite contained 3 microwave scanning beam landing systems, 3 gyroscopes, 3 TACANs, 3 accelerometers, 2 radar altimeters, 2 barometric altimeters, 3 attitude indicators, 2 Mach indicators, and 2 Mode C transponders. During reentry, the crew deployed 2 air data probes once they were traveling slower than Mach 5. The orbiter had 3 inertial measuring units, IMU, that it used for guidance and navigation during all phases of flight. The orbiter contains 2 star trackers to align the IMUs while in orbit. The star trackers are deployed while in orbit, and can automatically or manually align on a star. In 1991, NASA began upgrading the inertial measurement units with an inertial navigation system, INS, which provided more accurate location information. In 1993, NASA flew a GPS receiver for the first time aboard STS-51. In 1997, Honeywell began developing an integrated GPS /INS to replace the IMU, INS, and TACAN systems, which first flew on STS-118 in August 2007. While in orbit, the crew primarily communicated using one of 4 S-band radios, which provided both voice and data communications. 2 of the S-band radios were phase modulation transceivers, and could transmit and receive information. The other 2 S-band radios were frequency modulation transmitters and were used to transmit data to NASA. As S-band radios can operate only within their line of sight, NASA used the Tracking and Data Relay satellite system and the Spacecraft Tracking and Data Acquisition Network ground stations to communicate with the orbiter throughout its orbit. Additionally, the orbiter deployed a high-bandwidth Ku-band radio out of the cargo bay, which could also be utilized as a rendezvous radar. The orbiter was also equipped with 2 UHF radios for communications with air traffic control and astronauts conducting EVA. The Space Shuttle's fly-by-wire control system was entirely reliant on its main computer, the Data Processing System, DPS. The DPS controlled the flight controls and thrusters on the orbiter, as well as the ET and SRBs during launch. The DPS consisted of 5 general-purpose computers, GPC, 2 magnetic tape mass memory units, MMUs, and the associated sensors to monitor the Space Shuttle components. The original GPC used was the IBM AP101B, which used a separate central processing unit, CPU, and input-forward/output processor, IOP, and non-volatile solid-state memory. From 1991 to 1993, the orbiter vehicles were upgraded to the AP101S, which improved the memory and processing capabilities, and reduced the volume and weight of the computers by combining the CPU and IOP into a single unit. 4 of the GPCs were loaded with the primary avionics software system, PAS, which was Space Shuttle-specific software that provided control through all phases of flight. During ascent, maneuvering, reentry, and landing, the 4 PAS GPCs functioned identically to produce quadruple redundancy and would error-check their results. In case of a software error that would cause erroneous reports from the 4 PAS GPCs, a 5th GPC ran the backup flight system, which used a different program and could control the Space Shuttle through ascent, orbit, and reentry, but could not support an entire mission. The 5 GPCs were separated in 3 separate bays within the middeck to provide redundancy in the event of a cooling fan failure. After achieving orbit, the crew would switch some of the GPC's functions from guidance, navigation, and control, GNC, to Systems Management, SM, and Payload, PL, to support the operational mission. The Space Shuttle was not launched if its flight would run from December to January, as its flight software would have required the orbiter vehicle's computers to be reset at the year change. In 2007, NASA engineers devised a solution so Space Shuttle flights could cross the year-end boundary. Space Shuttle missions typically brought a portable General Support Computer, PGSC, that could integrate with the orbiter vehicle's computers and communications suite, as well as monitor scientific and payload data. Early missions brought the Grid Compass, one of the first laptop computers, as the PGSC, but later missions brought Apple and Intel laptops. Payload Bay, edit. The payload bay comprised most of the orbiter vehicle's fuselage, and provided the cargo carrying space for the Space Shuttle's payloads. It was 18 m, 60 feet, long and 4.6 m, 15 feet, wide, and could accommodate cylindrical payloads up to 4.6 m, 15 feet, in diameter. Two payload bay doors hinged on either side of the bay, and provided a relatively airtight seal to protect payloads from heating during launch and reentry. Payloads were secured in the payload bay to the attachment points on the longerons. The payload bay doors served an additional function as radiators for the orbiter vehicle's heat, and were opened upon reaching orbit for heat rejection. The orbiter could be used in conjunction with a variety of add-on components depending on the mission. This included orbital laboratories, boosters for launching payloads farther into space, the Remote Manipulator System, RMS, and optionally the EDO pallet to extend the mission duration. To limit the fuel consumption while the orbiter was docked at the ISS, the Station-to-Shuttle Power Transfer System, SSPTS, was developed to convert and transfer station power to the orbiter. The SSPTS was first used on STS-118, and was installed on Discovery and Endeavour. Remote Manipulator System, edit. Main article, Canadarm. The Remote Manipulator System, RMS, also known as Canadarm, was a mechanical arm attached to the cargo bay. It could be used to grasp and manipulate payloads, as well as serve as a mobile platform for astronauts conducting an EVA. The RMS was built by the Canadian company SPA Aerospace and was controlled by an astronaut inside the orbiter's flight deck using their windows and closed-circuit television. The RMS allowed for 6 degrees of freedom and had 6 joints located at 3 points along the arm. The original RMS could deploy or retrieve payloads up to 29,000 kilograms, 65,000 pounds, which was later improved to 270,000 kilograms, 586,000 pounds. Space Lab, edit. Main article, Space Lab. The Space Lab module was a European-funded pressurized laboratory that was carried within the payload bay and allowed for scientific research while in orbit. The Space Lab module contained two 2.7 m, 9 feet, segments that were mounted in the aft end of the payload bay to maintain the center of gravity during flight. Astronauts entered the Space Lab module through a 2.7 or 5.8 m, 8.72 or 18.88 feet, tunnel that connected to the airlock. The Space Lab equipment was primarily stored in pallets, which provided storage for both experiments as well as computer and power equipment. Space Lab hardware was flown on 28 missions through 1999 and studied subjects including astronomy, microgravity, radar, and life sciences. Space Lab hardware also supported missions such as Hubble Space Telescope, HST, servicing and space station resupply. The Space Lab module was tested on STS-2 and STS-3, and the first full mission was on STS-9. RS-25 engines, edit. Main article, RS-25. 3 RS-25 engines, also known as the Space Shuttle Main Engines, SSME, were mounted on the orbiter's aft fuselage in a triangular pattern. The engine nozzles could gimbal plus or minus 10.5 degree in pitch, and plus or minus 8.5 degree in yaw during ascent to change the direction of their thrust to steer the shuttle. The titanium alloy reusable engines were independent of the orbiter vehicle and would be removed and replaced in between flights. The RS-25 is a staged combustion cycle cryogenic engine that used liquid oxygen and hydrogen and had a higher chamber pressure than any previous liquid-fueled rocket. The original main combustion chamber operated at a maximum pressure of 226.5 bar, 3,285 psi. The engine nozzle is 287 centimeters, 113 in, tall and has an interior diameter of 229 centimeters, 90.3 in. The nozzle is cooled by 1,080 interior lines carrying liquid hydrogen and is thermally protected by insulative and ablative material. The RS-25 engines had several improvements to enhance reliability and power. During the development program, Rocketdyne determined that the engine was capable of safe, reliable operation at 104% of the originally specified thrust. To keep the engine thrust values consistent with previous documentation and software, NASA kept the originally specified thrust at 100%, but had the RS-25 operate at higher thrust. RS-25 upgrade versions were denoted as Block I and Block II. 109% thrust level was achieved with the Block II engines in 2001, which reduced the chamber pressure to 207.5 bars, 3,010 psi, as it had a larger throat area. The normal maximum throttle was 104%, with 106% or 109% used for mission aborts. Orbital Maneuvering System, edit. Main article, Space Shuttle Orbital Maneuvering System. The Orbital Maneuvering System, OMS, consisted of two aft-mounted AJ-10-190 engines and the associated propellant tanks. The AJ-10 engines used monomethylhydrazine, MMH, oxidized by dinitrogen tetroxide, N2O4. The pods carried a maximum of 2,140 kilograms, 4,718 pound, of MMH and 3,526 kilograms, 7,773 pound, of N2O4. The OMS engines were used after main engine cutoff, MECO, for orbital insertion. Throughout the flight, they were used for orbit changes, as well as the deorbit burn prior to reentry. Each OMS engine produced 27,080 N, 6,087 lbf, of thrust, and the entire system could provide 305 m/s, 1,000 foot/s, of velocity change. Thermal Protection System, edit. Main article, Space Shuttle Thermal Protection System. The orbiter was protected from heat during reentry by the Thermal Protection System, TPS, a thermal soaking protective layer around the orbiter. In contrast with previous U.S. spacecraft, which had used ablative heat shields, the reusability of the orbiter required a multi-use heat shield. During reentry, the TPS experienced temperatures up to 1,600 degrees Celsius, 3,000 degrees Fahrenheit, but had to keep the orbiter vehicle's aluminum skin temperature below 180 degrees Celsius, 350 degrees Fahrenheit. The TPS primarily consisted of 4 types of tiles. The nose cone and leading edges of the wings experienced temperatures above 1,300 degrees Celsius, 2,300 degrees Fahrenheit, and were protected by reinforced carbon-carbon tiles, RCC. Thicker RCC tiles were developed and installed in 1998 to prevent damage from micrometeoroid and orbital debris, and were further improved after RCC damage caused in the Columbia disaster. Beginning with STS-114, the orbiter vehicles were equipped with the wing leading edge impact detection system to alert the crew to any potential damage. The entire underside of the orbiter vehicle, as well as the other hottest surfaces, were protected with tiles of high-temperature reusable surface insulation, made of borosilicate glass-coated silica fibers that trapped heat in air pockets and redirected it out. Areas on the upper parts of the orbiter vehicle were coated in tiles of white low-temperature reusable surface insulation with similar composition, which provided protection for temperatures below 650 degrees Celsius, 1,200 degrees Fahrenheit. The payload bay doors and parts of the upper wing surfaces were coated in reusable Nomex felt surface insulation or in beta cloth, as the temperature there remained below 370 degrees Celsius, 700 degrees Fahrenheit. External tank, edit. Main article, Space Shuttle External Tank. The Space Shuttle External Tank, ET, was the largest part of the rocket and carried the propellant for the Space Shuttle main engines, and connected the orbiter vehicle with the solid rocket boosters. The ET was 47 m, 153.8 feet, tall and 8.4 m, 27.6 feet, in diameter, and contained separate tanks for liquid oxygen and liquid hydrogen. The liquid oxygen tank was housed in the nose of the ET, and was 15 m, 49.3 feet, tall. The liquid hydrogen tank comprised the bulk of the ET, and was 29 m, 96.7 feet, tall. The orbiter vehicle was attached to the ET at 2 umbilical plates, which contained 5 propellant and 2 electrical umbilicals, and forward and aft structural attachments. The exterior of the ET was covered in orange spray-on foam to allow it to survive the heat of ascent and to prevent ice formation due to the cryogenic propellants. The ET provided propellant to the Space Shuttle main engines from liftoff until main engine Q-TAF. The ET separated from the orbiter vehicle 18 seconds after engine Q-TAF and could be triggered automatically or manually. At the time of separation, the orbiter vehicle retracted its umbilical plates, and the umbilical cords were sealed to prevent excess propellant from venting into the orbiter vehicle. After the bolts attached at the structural attachments were sheared, the ET separated from the orbiter vehicle. At the time of separation, gaseous oxygen was vented from the nose to cause the ET to tumble, ensuring that it would break up upon re-entry. The ET was the only major component of the Space Shuttle system that was not reused, and it would travel along a ballistic trajectory into the Indian or Pacific Ocean. For the first 2 missions, STS-1 and STS-2, the ET was covered in 270 kilograms, 595 pounds, of white fire-retardant latex paint to provide protection against damage from ultraviolet radiation. Further research determined that the orange foam itself was sufficiently protected, and the ET was no longer covered in latex paint beginning on STS-3. A lightweight tank, LWT, was first flown on STS-6, which reduced tank weight by 4,700 kilograms, 10,300 pounds. The LWT's weight was reduced by removing components from the hydrogen tank and reducing the thickness of some skin panels. In 1998, a super lightweight ET, SLWT, first flew on STS-91. The SLWT used the 2195 aluminum lithium alloy, which was 40% stronger and 10% less dense than its predecessor, 2,219 aluminum lithium alloy. The SLWT weighed 3,400 kilograms, 7,500 pounds, less than the LWT, which allowed the Space Shuttle to deliver heavy elements to ISS's high-inclination orbit. Solid rocket boosters, edit. Main article, Space Shuttle Solid Rocket Booster. The solid rocket boosters, SRB, provided 71.4% of the Space Shuttle's thrust during liftoff and ascent, and were the largest solid propellant motors ever flown. Each SRB was 45 m, 149.2 feet, tall and 3.7 m, 12.2 feet, wide, weighed 68,000 kilograms, 150,000 pounds, and had a steel exterior approximately 13 millimeters, .5 in, thick. The SRB's subcomponents were the solid propellant motor, nose cone, and rocket nozzle. The solid propellant motor comprised the majority of the SRB's structure. Its casing consisted of 11 steel sections which made up its 4 main segments. The nose cone housed the forward separation motors and the parachute systems that were used during recovery. The rocket nozzles could gimbal up to 8 degrees to allow for in-flight adjustments. The rocket motors were each filled with a total 500,000 kilograms, 1,106,640 pounds, of solid rocket propellant, APCP plus BAL, and joined in the Vehicle Assembly Building, VAB, at KSC. In addition to providing thrust during the first stage of launch, the SRBs provided structural support for the orbiter vehicle and ET, as they were the only system that was connected to the Mobile Launcher Platform, MLP. At the time of launch, the SRBs were armed at T5 minutes, and could only be electrically ignited once the RS-25 engines had ignited and were without issue. They each provided 12,500 kN, 2,800,000 lbf, of thrust, which was later improved to 13,300 kN, 3 million lbf, beginning on STS-8. After expending their fuel, the SRBs were jettisoned approximately 2 minutes after launch at an altitude of approximately 46 kilometers, 150,000 feet. Following separation, they deployed drop and main parachutes, landed in the ocean, and were recovered by the crews aboard the ships MV Freedom Star and MV Liberty Star. Once they were returned to Cape Canaveral, they were cleaned and disassembled. The rocket motor, igniter, and nozzle were then shipped to Thiokol to be refurbished and reused on subsequent flights. The SRBs underwent several redesigns throughout the program's lifetime. STS-6 and STS-7 used SRBs 2,300 kilograms, 5,000 pounds, lighter due to walls that were 0.10 millimeters, .004 in, thinner, but were determined to be too thin to fly safely. Subsequent flights until STS-26 used cases that were 0.076 millimeters, .003 in, thinner than the standard weight cases, which reduced 1,800 kilograms, 4,000 pounds. After the Challenger disaster as a result of an O-ring failing at low temperature, the SRBs were redesigned to provide a constant seal regardless of the ambient temperature. Support vehicles, edit. The Space Shuttle's operations were supported by vehicles and infrastructure that facilitated its transportation, construction, and crew access. The crawler transporters carried the MLP and the Space Shuttle from the VAB to the launch site. The Shuttle Carrier Aircraft, SCA, were two modified Boeing 747s that could carry an orbiter on its back. The original SCA, N905NA, was first flown in 1975, and was used for the alt and ferrying the orbiter from Edwards AFB to the KSC on all missions prior to 1991. A second SCA, N911NA, was acquired in 1988, and was first used to transport Endeavour from the factory to the KSC. Following the retirement of the Space Shuttle, N905NA was put on display at the JSC, and N911NA was put on display at the Joe Davies Heritage Air Park in Palmdale, California. The Crew Transport Vehicle, CTV, was a modified airport jet bridge that was used to assist astronauts to egress from the orbiter after landing, where they would undergo their post-mission medical checkups. The Astrovan transported astronauts from the crew quarters in the operations and checkout building to the launch pad on launch day. The NASA Railroad comprised 3 locomotives that transported SRB segments from the Florida East Coast Railway in Titusville to the KSC. Mission Profile, Edit. Launch Preparation, Edit. See also, Launch Commit Criteria. The Space Shuttle was prepared for launch primarily in the VAB at the KSC. The SRBs were assembled and attached to the external tank on the MLP. The orbiter vehicle was prepared at the Orbiter Processing Facility, OPF, and transferred to the VAB, where a crane was used to rotate it to the vertical orientation and mate it to the external tank. Once the entire stack was assembled, the MLP was carried for 5.6 kilometers, 3.5 mi, to Launch Complex 39 by one of the crawler transporters. After the Space Shuttle arrived at one of the 2 launch pads, it would connect to the fixed and rotation service structures, which provided servicing capabilities, payload insertion, and crew transportation. The crew was transported to the launch pad at T3 hours and entered the orbiter vehicle, which was closed at T2 hours. Liquid oxygen and hydrogen were loaded into the external tank via umbilicals that attached to the orbiter vehicle, which began at T5 hours 35 minutes. At T3 hours 45 minutes, the hydrogen fast fill was complete, followed 15 minutes later by the oxygen tank fill. Both tanks were slowly filled up until the launch as the oxygen and hydrogen evaporated. The launch commit criteria considered precipitation, temperatures, cloud cover, lightning forecast, wind, and humidity. The Space Shuttle was not launched under conditions where it could have been struck by lightning, as its exhaust plume could have triggered lightning by providing a current path to ground after launch, which occurred on Apollo 12. The NASA anvil rule for a shuttle launch stated that an anvil cloud could not appear within a distance of 19 kilometers, 10 mi. The shuttle launch weather officer monitored conditions until the final decision to scrub a launch was announced. In addition to the weather at the launch site, conditions had to be acceptable at one of the transatlantic abort landing sites and the SRB recovery area. Launch, Edit. The mission crew and the Launch Control Center, LCC, personnel completed systems checks throughout the countdown. 2 built-in holds at T20 minutes and T9 minutes provided scheduled breaks to address any issues and additional preparation. After the built-in hold at T9 minutes, the countdown was automatically controlled by the Ground Launch Sequencer, GLS, at the LCC, which stopped the countdown if it sensed a critical problem with any of the Space Shuttle's onboard systems. At T3 minutes 45 seconds, the engines began conducting gimbal tests, which were concluded at T2 minutes 15 seconds. The Ground Launch Processing System handed off the control to the orbiter vehicle's GPCs at T31 seconds. At T16 seconds, the GPCs armed the SRBs. The Sound Suppression System, SPS, began to drench the MLP and SRB trenches with 1,100,000 L, 300,000 US gal of water to protect the orbiter vehicle from damage by acoustical energy and rocket exhaust reflected from the flame trench and MLP during liftoff. At T10 seconds, hydrogen igniters were activated under each engine bell to quell the stagnant gas inside the cones before ignition. Failure to burn these gases could trip the onboard sensors and create the possibility of an overpressure and explosion of the vehicle during the firing phase. The hydrogen tanks valves were opened at T9.5 seconds in preparation for engine start. Beginning at T6.6 seconds, the main engines were ignited sequentially at 120 millisecond intervals. All three